Today we will be discussing about how to build neural network with the help of a very widely used library named Keras. So the topic of today's meetup is building neural network with Keras. And so before introducing to our speaker, let us first we would like to welcome you with the video of Andrew NG, where he will welcome you with himself. So, here it is.
Hello, deep learners. I'm Andrew Ng, founder of deeplearning.ai, and I'm excited to welcome you to our global deep learning community. I know that many of you are here today because you want to break into AI and build your career. I hope that being part of this community will help you to do so. To give you a proper welcome, I'd like to show you around the deeplearning.ai offices and meet some of the teams so that you can see where it all happens.
Oh, hi, Andrew.
Um, do you want to tell our friends at Pine AI what you do at deeplearning.ai?
Sure. Hi, everyone. I make articles and other media that help people learn about AI and help them understand the huge impact that AI is having in the world. Today, I'm putting together the next issue of The Batch, our weekly newsletter, and I'm looking for the biggest stories of the week to keep our readers informed.
What's been the most surprising thing you've run into working on the batch?
How much is going on in this field? There's never a dull moment. You know, you might think from the outside that machine learning engineers really understand everything about AI, but nobody understands everything about AI because this field is just coming to life right before my eyes as I put this thing together every week.
All right, I know you're really busy, so let you get back to it.
Thanks. See you later.
Let's go meet Kian, who helped me create the deep learning specialization. He's working on an exciting new project. Hey Kian, so do you want to tell the people at Pine AI what you're working on?
Yes, sure. I'm leading a project called Workera, focusing on helping people get offers in AI and navigating their career by testing their skills, preparing for interviews and certifying them, as well as matching and referring them to good jobs in AI.
That's really cool. And what's the most exciting part of your day?
You know, the AI field is new, organizations and jobs are still misunderstood. So I'm excited to help people understand what different types of jobs exist in the field, what tasks they will work on, and what skills are needed to achieve those tasks.
That's really important work. Well, it's nice chatting. And now let's go chat to Hotel, who is on their product team.
Hey, Andrew.
Do you want to say hi to our friends at Pine AI and let them know what you're working on?
I would love to. Hi, everyone. I lead the product team in deeplearning.ai, where we create AI education content accessible to people all around the world. People like you.
And what are you most excited about right now?
I am so excited to see our community grow and to see how eager people are to learn more about AI.
Thanks, also.
Thanks, Andrew.
So as you can see, our team is working hard to support you and help you learn. It's never been easier than before to break into AI. So if you want to build a career, you can leverage online resources available, including open source code, datasets, papers, and online courses like a deep learning specialization on Coursera. As part of this journey, I hope you get your hands dirty too. Don't be afraid of diving in to build your own project. Or go ahead and try to replicate a research paper that you're excited about. One thing that I've seen help a lot of people succeed is if you can build a community or find a community of fellow deep learners you can meet with and study with on a regular basis. In fact, I hope that this Pine AI meetup that you're at right now will be a good place for you to meet these people. I hope you enjoyed the event today and that you learn a lot, both from the talks and from each other. And once again, welcome to the deeplearning.ai community.
So, welcome everyone in the community of deeplearning.ai. So, let me introduce the speaker. that is Debolina Mahapatra ma'am, and she will be guiding you from here. The to all the rest of the session, and she will be I we know that she will be a better guide for all of your journey, just like the previous one. So a little about herself. She is M.Tech scholar of NIT Patna in Department of Computer Science and Engineering with the specialization in information security, and her research areas are deep learning and NLP and social network analysis. So without wasting much of the time, let us proceed to the session part. So I would like to welcome Debolina ma'am for the rest.
Hello everyone. Hi, so thank you to Pi and AI Patna for organizing this session. And we all know that understanding the mathematics behind any learning algorithm is much more important than actually knowing how to implement it in any programming language, right? Which is why in this session we are going to see how neural networks work and how we can implement it using Keras library. So Keras is a very popular library, and it is much simpler because you can build your neural networks in supposedly a human like conversation like language. So it is really fun building neural networks using Keras. But yes, after understanding the mathematics behind the working of neural networks, it won't seem like a black box to you. So this is just a little bit about myself, and I am presently pursuing my master's at NIT Patna, and I have worked in areas of deep learning, NLP, and social network analysis. And I'm currently working in an area which is a blend of information security along with applied deep learning. Like most of you present here today, I am an AI enthusiast and I love to learn and explore different domains of AI. So let us begin today's exciting session on neural networks, and also we will build a recognizer together. So stay tuned till the end. Okay. And I also wanted to know how many of you have previously worked with neural networks. If anyone has worked with neural networks, then do raise your hand. Do we have anyone? Okay. Yes, so we have one person. Okay. All right. Neural networks is actually a very popular learning algorithm in today's time, and it is because it kind of acts as a launch pad to your deep learning. So neural networks forms the foundation of deep learning, and we will go through just a brief history of neural networks. So first of all, it started all in the 90s. So we had McCulloch-Pitts neuron, and later on we had Rosenblatt, and it just went on progressing. And today we have our deep neural networks, which have tremendous capabilities. Okay, so these are three interrelated areas, and there's a quite of, I would say, confusion among people. What is what? So here we have a Venn diagram which actually separates all of it. So artificial intelligence is the broader area, and it includes any technique that enables computers to mimic human behavior. So computers can learn to, for example, computers can learn to recognize a cat from a dog. So that is what AI does. And machine learning gives computers the ability to learn without explicitly being programmed for. So our learning algorithms try to find the implicit patterns, the patterns which are hidden within the data, in order to reach that learning outcome. And deep learning is based on extracting patterns from data using neural networks. So we may ask the question that why is there such a hype about neural networks? Why does everyone want to learn about neural networks? And why is there such a hype about deep learning? So we all know that neural networks existed since a very, very long time. So how is it that all of a sudden it just became so popular? So the thing is that before in the 90s, we did not have such good computational power. So in older learning algorithms, you must have seen that you don't have such complex architecture, but in deep learning you have that. This is because nowadays we have access to GPU techniques. We have accelerated training using GPUs. And this GPU enables us to have deeper and larger network architectures. And also, with as the time has gone by, we have also seen that there has been a lot of increase in the amount of data. So nowadays you see that everything is online. So people are sharing huge amounts of information online. So in order to process such huge amount of information, we also need deeper and larger architectures, which is why deep learning has become more powerful in the present age. And these are some of the applications that you must have heard. And these applications are supported by neural networks and deep learning. So first application we have is character recognition, image compression, then stock market prediction, medical image analysis. So this is one of the most important applications that I personally feel, because medical images are quite complex to understand for any normal human being. It has to be analyzed from the perspective of a doctor. But with deep learning, we can have such advanced systems that enable us to analyze these medical images and build automated systems. So you can have systems such as detecting cancerous cells from the scans. So that is a very powerful application of deep neural networks that I personally feel. Then we have handwriting recognition, face recognition, another powerful application, self-driving cars, and there's just a lot more. So in this session, we are barely scratching the surface. There is so much to learn about neural networks, and we are only on the surface level this time. So, you must have heard about backpropagation. So, this is the core algorithm behind neural networks. But understanding backpropagation is a bit complex because you need to have a lot of mathematical background. You need to understand matrix manipulation. You have to go through a lot of calculus. So in this session, I have tried to minimize the complexity of equations and have just given a brief overview of what calculations are being done in order to reach the output. So over here, we have an input layer, and in this input layer, we have two neurons in the input, and then we have two neurons in the hidden layer and two in the output layer. So we only have one hidden layer present. And you must be seeing that there are connections between the input neurons, the hidden layer neurons, and the output layer neurons. So these connections are actually containing the weights. So we have weights which help us to train, and we manipulate these weights in order to enable the learning process. Okay, so this is the initial configuration of a numerical example. So like I told you, I would not go into the mathematical equations and everything. So I'm going to explain you with the help of a simple example. So we have two inputs, like I said, I1 and I2, and these are the values. And we have the bias, the weights, and the input to hidden layer given as all the values, and the inputs from the hidden layer to the output layer. Sorry, the weights. So the weights we have over here. And what actually happens is that we have a summation function. So over here we feed in the weights and we compute the summation, which is wixi, the that I would say the cumulative summation of, and we find, and this particular summation that we obtain, we will feed it to the activation function, and after what we get from the activation function, that serves as the output of our neural network. So let's see this. So first step is finding the linear combination of the input signals. So over here we had several weights that you saw along with the input layer neurons that we had, and we will add up the bias at the end. So over here in this equation you have ij, which refers to the inputs, the input layer, wkj, which means that these are the respective weights of the neuron k, and bk is the bias, and vk is the linear combination of the input signals. Then okay, so here we have a bit of mathematics, and I would like you all to try it out on your own. So we can have a matrix representation. So matrix operations help us to further simplify the calculations. So instead of having the single equations and solving the equations one at a time, what we can do is that we can have matrix manipulation. So we can have W transpose X plus B. So W transpose actually gives you the weight matrix. So whatever weights that we have. So first we had the weights between the input layer and the hidden layer. So all those four weights can be put into a single matrix. Then we will form the transpose of that matrix to finally attain this particular, I would say, equation pattern that helps you obtain the summations. So over here we had W1, W2, W3, and W4. Then we form the transpose, we get the matrix, then we multiply it with the input, the whatever inputs that we had. So I'll take you to the previous diagram. So over here, you can recall that we have W1, W2, W3, and W4. So these are the four weights between the input layer and the hidden layer. And utilizing these weights, we will go on manipulating the computations. And yes, so here you have the inputs to hidden layer and all the weights along with the values, and we will go on, we will compute the linear combination. So over here you can see the particular matrix. So we can have all our values, multiply it and sum it. And you have to work out on your own. You will work out on your own and you will see what values you get. And that is how, this is the basic level forward propagation that the neural network actually does. But yes, over here we have only two input values, but a neural network operates on a large data sets. So this is one step, and now we are going one step further. So after this, so so after this, we have step 2, which is we apply the activation function. So activation function is actually a mathematical equation that helps us to determine the output of a neural network. And it helps us to understand whether a particular neuron should be fired or not based on whether each neuron's input is relevant for the model's prediction. So there are lots of activation functions available. Most popular is ReLU, rectified linear units, followed by sigmoid. Then you also have softmax, and a lot of activation functions are available, which you can try it on your own. So as you have to choose your activation functions as per whatever application that you want to achieve. So for example, a simplest activation function is rectified linear units, ReLU, which actually takes the maximum of 0 or the number. So it is a piecewise linear function. So for all inputs which are 0 less than 0 will be mapped to 0, and all inputs which are greater than 0, they will be mapped to their that will be served as an identity function. So likewise, we have a lot of activation functions, but today we are also going to discuss a lot of implementation, which is why I'm not discussing them right now. But if time permits, we'll also see a few of them. So this is the core thing, which is the backpropagation algorithm. And what it does is that it looks for the minimum value of the error function. So what we try to do in neural network training is that we want to minimize the error value. And this minimizing the error value, this particular technique is also known as gradient descent, or you may also call it as delta rule. So when the weights that minimize the error function, then we consider them to be a solution to the learning problem. So until and unless we have a set of weights that achieve the minimum error, then till that point, we go on iterating through the forward propagation and back propagation. So this loop goes on and on and on until and unless we can reach the minimum point of on the error function. Okay, so this is the mathematical point of view. So first we had computed the linear combination over here. So z equal to w1x plus b. After that, we went to the activation function. Right. So for this particular thing goes on until we finally arrive at the output. So what happened between the input layer and the hidden layer, the same approach will be applied between the hidden layer and the output layer until we arrive at the final output. So here we got the final output and then we computed our error. So whatever error that we got, we have to propagate. The error propagates throughout the entire network, so that we need to understand. And over here we have some differential calculus notations, which I won't discuss in detail today, but if you have to compute that for each how much change actually takes place, like whatever error that you obtain, how is that error impacting the network. So you go step by step and you compute it. So what del L and del A2, what it tells you is that what change, so how the error is changing and how this change in error is having an impact on your network. So that is the core of your back propagation algorithm, the how the error is propagating in the network and how is that error affecting your network. So like that the loop goes on until and unless you can arrive at that minimum error point. Okay, so this is the gradient descent. So we have something known as the learning rate. So learning rate is applied over here. So whatever you see over here, that eta, so eta is actually your learning rate. And in gradient descent, what we do is what is done is that we have this error function. So what you see over here is the error surface, and we try to find that point on the error surface such that it is the minimum point, the lowest point on the error surface. So, okay, I hope my cursor is visible to you. So suppose you have a point over here, the starting point. So the updation in the weights will take in such a way that the error will move from the highest point to the lowest point. So that will be the converging point and the training will stop. So that is the gradient descent rule. And okay, so now we will move on to the implementation part. Okay. Is my screen visible? Can anyone tell me? Is the Google Colab visible? Hello?
Hello.
Yeah, is the Google Colab visible?
Yeah.
Okay. First I'll show you how can we use Keras to build our own neural network. So Keras is basically a wrapper around a backend library. So a backend can be your TensorFlow, Theano, and Cafe, or so on. And Keras follows the best practices for reducing the cognitive load. So it is when you go to the website of Keras, you will see that it is they have written it in bold, right? It is designed for human beings and not machines. So why is it? Because of its ease of usage. So here we have a simple neural network, and we can take two numbers as input, and we pass them through a hidden layer of 10 neurons. So our input layer consists of two neurons. We pass them to through a hidden layer consisting of 10 neurons, and finally a single number as the output. So you have these libraries in Keras. So first we will import from Keras.models. We will import the sequential model. Sequential model because we are going to add on top of the other. So we will have layers. So first we will have one layer. We will add the next layer on top of it, stack it. So that is why we have this particular library. Dense because we are going to add all the number of neurons in that. So that is why we have this dense layer. And first we will create a sequential model. We will add an input layer and a hidden layer with 10 neurons. So over here in dense, when we are initializing it, so you have the option to mention the input shape. So whatever is the shape of your input layer. So here as we have two numbers as the input, so we mention input shape is equal to 2 comma. So that is the way you will mention the input shape. And we have 10 neurons in the hidden layer. So we mention 10 over here. And for this particular network, I am using ReLU activation. So you will mention your activation function, but instead if you wanted to use a different activation function, you can always change it. From ReLU, you can use sigmoid or any other activation function. And again, we add one more layer on top of it. So why do we do that? Because it is the output layer. So we have a single neuron as the output. So we will add model.add dense 1. So when we are creating a sequential model, it does not have any layers over here. But when we are doing model.add, the first layer that we have along with the input layer defined within the dense layer. And then on top of that, we also have the output layer. So when you do model.summary, it looks something like this. So we have the dense layer, first layer, and the second layer. So you might want to understand how the computations are taking place. So in the dense layer, we had two neurons, right? And when we have 10 neurons in the hidden layer, so what happens is that each of the neuron in the input layer will be connected to each of the neuron in the hidden layer. So 2 into 10, so we will have 20 weights over there. Along with that, we will also have a bias weight. So for the bias weight, we will have another 10 connections. So 20 plus 10 and we get 30. Similarly, when we want to compute the number of weights between the hidden layer and the output layer. So in the hidden layer, you have 10 neurons, and in the output layer, you have just one connection. So 10 into 1. So we have 10 weights plus 1 for the bias. So bias will also have a connection with the output layer. So you have 1 and we get 11. And then if you see, the total parameters are 30 plus 11, which is equal to 41. So that is the way you can see how the different parameters are getting computed. So it is actually based on the number of weights that we have. And you can also visualize your whatever model that you have built. So we have the input layer over here, then the dense layer, which is the hidden layer, and lastly we have the output layer. There's also a very good library called ANN Visualizer, which I often use to visualize my neural network. So here I'll show you the output that I got from the visualizer. So this is the model that we just built right now. So we have the input layer, and then we have the 10 neurons in the hidden layer, and then we have the output layer. All right. So we will now, I hope this part is clear. So we will now proceed to digit recognition application, which is we are going to do on the MNIST data set. So the MNIST data set is actually available in Keras datasets library. So you can directly import it. You do not need to download the entire data set while working with Keras. It's pretty easy. And then we have, yeah, so over here, if you want to visualize your the images that we have, so MNIST dataset is actually consisting of all the picture handwritten digits. So this is quite used for handwritten digit recognition. It is a very popular app, popular data set, and we also call this particular application as the hello world of deep learning. So it is popularly known as the hello world of deep learning. So let's see what we have over here. So these are the way all your inputs are inputs appear in the data set. So we have 60,000 inputs in the train data set and 10,000 in test set. And each of the image is 28 cross 28 pixels. So you can see that these are all black and white images. So uh, has anyone worked with images? Can I have anyone from the audience? Has anyone worked with images? Okay. Um, okay, no problem. So when you have an image, we also have what are called as channels. So for grayscale images, we have only one channel, whereas if for colored images, we have three channels, which stand for RGB, red, green, blue. So over here, so for our images, we have only one channel. And image dimensions, if you can see, we are going to compute it, we are going to first flatten the image. So you cannot actually apply your neural networks without reshaping your image. So you first have to reshape your images. So what I have done is that I have reshaped it to a single channel. So in image size, we had 28. So I performed 28 cross 28. Then we have 784. And I reshaped it to have the value 60,784. So 784 is the dimension of my image after I have flattened it. So that is the first pre-processing step that you need to perform. And after that, one more thing is that we have to do is you have to normalize your images. So whatever pixel values that we have can be in any range, but we have to normalize them in the range of 0 to 1. So 255 is the max so range that pixels can attain. So we normalize them so as to have the range between 0 and 1. Next, we will define our model. So we have 256 hidden units in our model, and we define a batch size to be 128. So this might seem a bit complex than the previous one, but I'll explain it step by step. So we have these layers over here you have. So some of which I'll explain in a subsequent session. Some layers need some more explanation. So dropout and a few other things. But dropout is actually we are dropping out some of the neurons so as to avoid overfitting. So for now, just understand that the dropout layer is used to avoid overfitting in neural networks. Okay, so we are having two hidden layers over here. And first, we have already defined our hidden units to be 256, and the input dimension we already had as 784. So we also mentioned the input dimensions over here. So that is how you define the first hidden layer. And we have mentioned our activation. So you can mention your activation within the dense function as well, but I have added the activation separately like a layer. It does not make any difference, but it's just a convention that I like to follow. And you have the dropout along with the dropout rate. So we will skip this part in this session, but in a subsequent session I'll go into much detail. So this was your first hidden layer, which has already been done. Now on top of that, we also add one more hidden layer. So the other hidden layer is over here. So you do not need to mention the input size anymore. You can just add the subsequent layers one after the other. And we have the activation again as ReLU. And at last, we have the output layer. So for the output layer, we will use the softmax function. So a softmax is actually used to for multi class classification. And so as we have 10 classes over here, so we will use this activation function to identify so in which particular class our sample belongs to. And you can see how a model actually looks like. So you have a first hidden layer, the second hidden layer, and the last layer, which is the output layer. And this is just a small visualization of the same. Okay. And there is one other function which you have to perform when you're training the model using a data set. So model.compile. So we are compiling the model. We are giving the parameters in the model. So what loss we will be using? So here we are using categorical cross entropy loss. So these are some of the terminologies. If you are a beginner in deep learning, so this may seem out of the box right now, but in other subsequent sessions, I'll go through all of it in much detail. But for now, I just wanted you to understand how this all works. So you have to define your loss function. So loss function is actually the how our error is being computed. All right. So this is the categorical cross entropy loss for this particular application. Then optimizer as Adam. So you also have an optimization function, and the metrics on which it is being applied is accuracy. So accuracy of the model. After that, we will perform model.fit function on the normalized train samples that we have. Y train, epochs is how many iterations you want to run your neural network, so how many times you want to train the network. So here we have defined epochs to be 20, and batch size we already have defined. So when you see in the end, for each step, the loss and the accuracy is being computed. You can see the training is quite good because the loss was initially 0.73 with the accuracy of 0.76. But as we proceed, we can see how the loss has decreased and the accuracy has increased. So that is the core part for your neural net for neural networks, or you can say the core of the gradient descent. Gradient descent, what does it want to do? Gradient descent wants to minimize the loss and maximize the accuracy. So you can actually see in action how it is being performed. We can see the loss to be 0.05 and the accuracy is 98%. So when we evaluate the model on the test data, so we see the model achieves the accuracy of 98.2%. You can also see other metrics in the model. So when we there's this particular function called predict classes. So that will help you to get rather than testing for each and every the class over here, like it's collectively, you can also get the individual classes over here. So for predict classes, we get 7, 2, 1, 0, 4. These were the handwritten digits. So whatever digits you have, so the model is accurately predicting or not. So you can just see. And here we have a confusion matrix along with the accuracy score. So 98.18 and the classification report. So per class, so you can see your precision, recall, F1 score, support. So all of it you can analyze your own on your own, whatever application you are performing. So this was all I had today. If anyone has any questions, you can ask me. Hello. Do we have any questions? You can ask in the chat box.
You can unmute and ask any of the questions you want.
You can also post your questions over here.
Good evening, ma'am.
Hello, good evening.
Yeah, ma'am, I did install TensorFlow, but it's not detecting my GPU. So how to change the
Okay.
settings?
Are you having a local installation?
Yes, I did install it using Conda install.
Okay, I won't be able to resolve it right now, but if you can share your screen sometime, then I'll see to it.
Okay.
Because it totally depends on what error you are getting. But if you
No,
want to,
it's actually not showing error. There's a command in TensorFlow to see
okay.
the available GPUs. So it's showing none.
Some settings, maybe you have to look after some of the system settings or add it to the environment variables. Uh, like that, it may resolve. So I can't I can't suggest you anything until and unless I go through the system. But if you are having certain issues in implementing, then you can always go for Google Colab. So over there you can you have your GPU readily available, so you can connect it over there. You can do your work, and later on we can see how we can resolve it.
Okay, ma'am. Thank you.
Okay. Any more questions? Any participant, if you have any questions, you feel free to say. I know this was actually quite a tricky thing, the mathematics part, and just because I also had to go through the implementation, I was not able to compress all of that mathematical information into one presentation. But we will have a part two of this session as well, in which we will go through the rest of it. So if no one has any questions, I'll like to show you some of the activation functions that we have. Uh, I'll wait if anyone still has any questions, and if you're hesitating to ask, then no worries. You can just unmute yourself and talk to us. Okay. Okay, then I'm assuming that no one has any questions. So, okay, so let's see some activation functions. Uh, is my screen visible?
Yes, it is.
Okay. So this is what I was talking about, ReLU activation function or the rectified linear units. So this is how the function actually looks like. So you can see it is a straight line along the x-axis. So the value is actually 0. And for all of the inputs which are greater than 0, 0 or greater than 0, so it will be mapped to the input itself. So that is y equal to x. Over here you can see. And pros and cons over here, you can see that ReLU, it rectifies a vanishing gradient problem. So there is a particular problem with gradient descent, which is called vanishing gradient problem. And that is the reason why ReLU is so popular nowadays, because this is quite robust, we can say, and it is used to encounter such issues within the neural network, and it is also less computationally expensive. So you also have certain functions, activation functions like tanh and sigmoid, but they involve a lot of mathematical computations. A lot of mathematical computations, but ReLU is comparatively very simple, and there are certain limitations as well in ReLU. So sometimes it blows up the activation function. Is
माइक्रोसॉफ्ट डॉट नेट इंस्टॉल करना है.
okay? Is someone saying something?
हाँ मेरे.
Okay. Okay, never mind. Then we also have the leaky ReLU function. So these are several different kinds of activation functions that you have, that you can use for your own application, for your own projects. So we also have leaky ReLU function. So this is just a modification of the existing ReLU. And you have a small non-zero constant gradient alpha, which is applied over here. So what ReLU did is that it did not have anything. It just used the identity function. So y is equal to x is called the identity function. So for all values which are greater than 0, simply apply the identity function. So that was what happened in ReLU. But in leaky ReLU, what we have is that we also have a parameter applied. So it kind of uh, it's different, of course, and the it's what it does is that it fixes some of the issues existing with ReLU. And next we'll move to the sigmoid activation function. So sigmoid activation function has been used for quite a long time, and it takes a real value, and the output of the sigmoid activation function is a value which lies in the range between 0 and 1, and it is quite easy to work, but again it is computationally extensive. And we can see this is the graph for the sigmoid function, and the equation for it is 1 by 1 plus e power minus e. So it is non-linear, and it's good for a classifier, and it is even used in neural networks. So whenever we have to predict the probability values, often we use sigmoid activation function in the layers of a neural network. And the gradient is also smooth, and again, with sigmoid activation function 2, we have the vanishing gradient problem, and I'll go to that one later. And this is the tanh function. So these are the different kinds of activation functions. So sigmoid and tanh were a lot used in previous applications, but nowadays mostly you see ReLU. Sometimes you see the sigmoid activation function, and mostly in the output layer you'll also always see the softmax activation function in almost of the multi-class classification problems. So what tanh does is that it squashes a real valued number, so in the range of -1 to 1. So in sigmoid you had 0 to 1, in tanh you have -1 to 1. And this is how it looks like. And yeah, so this one you have softmax activation function. So what it does is that it calculates the probability distribution. So you have n different events, so it will calculate the probability, and it will tell you that which target class is more probable over all possible target classes. So that is how the softmax works. All right. So these are the various kinds of activation functions that you can go through on your own. You can experiment it, and after working, you'll slowly get the hang of Keras and how it works and what all you can do with that. So here, as this is a very simple way to build a neural network. You only have to specify your the architecture and your data, whatever data you have, and then you can simply analyze it. You can fine tune your own network and so on and so forth. If anyone still has any questions, then feel free to ask, or we'll end the session. Does anyone from the audience has any questions for us? Okay, then.
Ma'am,
Yeah. Yes, yeah.
ma'am, neural networks are also several types, na, isn't it? Artificial neural
Yeah,
networks,
yeah.
neural networks. What are those?
So artificial neural network, the name of neural networks was initially artificial neural networks. So why is it known as artificial is that it has some biological motivation to it. Okay, so biological as in it was based on how a human brain actually works like. So if you have studied biology, then you'll know that our brain cells, everything is composed of what are called as neurons, right? So the interconnection of neurons is how signals travel within our entire body. So if you wave your hand at someone, then there is an instant rush of the pulse from, so it is kind of I would say the neurons are activating it. So everything that you are reading about in neural networks, it has its inspiration, its biological motivation from how the neural network within our own body actually works. So that is why it was named as artificial, the term artificial neural network. But it just has the biological motivation, but it does not do anything like that. You just now you saw that the neural network, it actually has all mathematical functions within it, but the motivation behind developing the neural network actually comes from the biological neural network. So that is what your ANN is. Yes, and there are many different types of neural networks. So I'll have each and every session, subsequent session, we will be discussing the different types. So we have convolutional neural networks, then we have recurrent neural networks, we have auto encoders, and nowadays we also have a lot more than that, which I won't mention right now, but we will discuss in the subsequent sessions. So a convolutional neural network is more popularly used for image applications. So what you have to do is that it's very simple to work with, because it acts like a black box to most people. What it does is that it will identify the hidden patterns, CNNs. So CNNs are very robust, and it can work with a lot of data. It can find patterns within the data very easily, and that is why in most of the image based applications, image recognition based applications, we use the convolutional neural networks, because it's not really possible to define handcrafted features, especially for image data. But with CNNs, we can have a very powerful applications based on image data. So face recognition, then object detection, OCR. So you can do all of that with a very high accuracy using CNNs. Then comes the recurrent neural networks. So it works in a feedback mechanism, and you have LSTMs, long short-term memory models, and there are there are GRUs and a lot more. So the field of neural networks is just so vast that I cannot talk about it in just um, one single session. We need to have like 10 sessions if we want to cover, if even if we want to dive into the ocean of neural networks. So there's just so much to learn from it. That's all I'll say right now. These are the networks that I can tell you about. But in subsequent sessions, we'll dive deep. We will see how image recognition applications are being taking place, and LSTMs, which is actually a branch of recurrent neural networks. So LSTMs are also very good in text-based applications. So when we will go through the how to compute embeddings, word embeddings, and a lot more. So we will see how LSTMs are actually applied. So in subsequent sessions, we'll go through all the different types of neural networks. Don't worry.
Okay, ma'am. Thank you, ma'am.
Okay. Anyone has any questions? Anything you want to know? Anything you want to ask? So I hope you all understood how we can use the Keras library to build our own neural network. And the neural network should not be a black box to you. You should understand what is going on, what computations are actually operating behind the scenes. So that was the prime motivation why we had this webinar, because you need to know what forward propagation is, what back propagation means, and how the error surface gets generated, how the gradient descent is operating, and it tries to reach the minimum point on the error surface so as to minimize the error in your network. So these are some of the things that you must know before you try to implement neural networks on your own. And also, some mathematical background is required in order to understand the functioning of the networks. So as mathematical background, I'll say just some calculus and some probability theory. If you know, And we also have matrix-based calculations. So matrix manipulations are quite simpler to understand, which is why while we study neural networks, we can simply go for the matrix-based manipulations to understand the computations and how they are working. And in today's session, we also saw the digit recognition application. So in digit recognition, we saw how we took the MNIST data set and we took the images, which were 28 cross 28 pixels, and all of them were grayscale. And we also understood how pre-processing was done. We flattened the image into an array of 784 values and we fed it to a neural network. So we had our own neural network and it had two hidden layers. And using that neural network, we achieved an accuracy of 98.2%. So I hope all of you had fun attending this session, and we'll be sharing the notebook with you. We'll be sharing the uh, Python notebook. I'll drop the link just now. So thank you to all of you, and thank you to Pi and AI Patna for organizing this event.
Thank you, ma'am.
Thank you, ma'am.
Thank you.